Good afternoon, ladies and gentlemen. I'm Roderick Flood, the Provost of the College, and as usual, I'm delighted to welcome you to a Gresham lecture, but this is a particularly special one, in that this is the inaugural lecture of our new Gresham Professor of Astronomy, Carolin Crawford. I'm not going to take up any more time other than to say that, as I have discovered in appointing Gresham Professors, we have fields which any university in the world would die for. So Carolin beat off some extremely strong competition with her presentation on that occasion when we interviewed her, and I'm sure that's a great augury for the quality and interest of the lectures that she'll be presenting to you, starting with this one. So, our new Professor of Astronomy.
Thank you very much for that lovely introduction. It can only go downhill now, really, can't it? So I've chosen as my topic today Saturn, all about Saturn, its rings and its moons, partly because as an opening lecture you're going to see some beautiful imagery, real images of Saturn and all its environments. But also Saturn's one of those objects that really does capture the human imagination. It's the most distant of all those wandering stars that the prehistoric people used to watch. And could, with the unaided eye, it's the furthest planet that we can see without aid of telescope or binoculars. And it has exerted a pull on our ideas. And of course, none more so than when we discontinued looking with just the unaided eye, but when it was first viewed through a telescope by Galileo in 1610. And Galileo, this mastermind who worked out that there were hills and valleys on the moon, that there were little satellite moons that went around Jupiter, that the Milky Way was full of stars, he was flummoxed by Saturn, because Saturn seemed to change its mind, seemed to change its appearance. So when he first looked, he described it, you can see a little diagram here, he described it as kind of being three objects. So it looked like one large object, maybe with a couple of moons. And when he next examined it, a couple of years later, those features had completely gone away. And then later on, by about 1616, when he looked at the object Saturn again through his telescope, it had changed. It no longer seemed to have, these two moons to either side of it. He described it as having arms, or like cup handles to either side. And he really didn't understand what it was that he was seeing. And a real interpretation of what this kind of extended shape was didn't come along until telescopes were improved later in the century, when the optics were so vastly improved that when Christian Huygens turned his telescope onto Saturn, he could clearly detect and ascertain that these were rings. They weren't moons, they weren't cup handles, these strange structures were rings. And not only did he identify the rings, but he also found Saturn's largest moon, Titan. He discovered that. And then only a few years later, Jean-Dominique Cassini, the Italian-French astronomer, again, better telescope, looked at Saturn and its rings, and by now he's finding 4 more large moons in orbit around Saturn. And not just that, when he looks at the rings, he sees their structure within them. He sees dark bands, separation, not just solid rings, but there are marks within them. And he's intrigued. Now, of course, now, we don't have to rely on telescopes anymore. We have the luxury of being able to go to Saturn and observe it in situ via our spacecraft. And surprisingly, there have only been 4 spacecraft sent to Saturn. The first one was Pioneer 11, which flew past Saturn in 1979, closely followed by the 2 Voyager spacecraft in 1980 and 81. And I'm sure you've nearly all seen this iconic picture of Saturn with the Voyager spacecraft. I remember, somewhere I still have got my copy of New Scientist that had this on the cover from the early 1980s. I was so gobsmacked by this picture. And, Saturn is an inspiration for me. It's one of the reasons I've chosen it as my first lecture, because at that point I was deciding what A-levels I was going to do. I was going to decide what I was doing for the rest of my my life. And it was just seeing how much there was still to be discovered, even within our own solar system, was so exciting that, you know, images like this were one of the first things that actually really pushed me to decide to become an astronomer myself. Of course, those were flypasts. There is one fourth satellite which has been in orbit around Saturn since 2004. This is the Cassini spacecraft, named after one of those eminent astronomers who discovered stuff about Saturn. Now, this took a 7-year voyage to arrive at Saturn, and it's been in orbit around the rings and the moons and the giant planet itself since then. The original mission was only going to be for 4 years, but it's been so successful, it's been renewed twice. And so all the images, I think, apart from a couple of diagrams, and I will tell you when there are diagrams, not real images, all of the images you're going to see within this presentation are taken from this Cassini spacecraft. It was a joint mission between the American Space Agency, European Space Agencies, a whole conglomeration of nations, probably about 14 nations combined, inputting experiments and expertise into the spacecraft. And I had a whole suite of different scientific instruments. You'll hear some of the results from them as we go along. But primary ones, certainly for this talk is concerned, were cameras. Cameras that image Saturn and the rings and moons, not just in visible light, but also near-infrared, ultraviolet light, telling us different things about the structure and the depths within the planet. So let's go to Saturn itself and just start off with some statistics. You all know it's the second largest planet in our solar system. It's the 6th one out from the Sun. That means, in terms of how far it is out from the Sun, it's just under 10 times the distance between the Earth and the Sun out to Saturn and the Sun. And when it's out there, it goes around the Sun very slowly. It takes a whole of 29.5 years to make it once around the Sun. And not just that, it's so far away from the Sun, it's so much colder. There's only like 1% of the light that reaches Earth actually falls on Saturn. So it's much colder. The average temperature here within its atmosphere is something like minus 180 degrees C. It's very cold. And the actual size of the planet itself, well, you could probably fit about 9.5 Earths from one side to the other. In fact, if you pack together 760 Earths, they'd fit inside the volume of Saturn. I'll then tell you also, in our statistic, the mass of the planet is 95 Earth masses. And if you actually think about those numbers for a minute, you think, well, you've got 95 Earth masses packed into a volume that's 760 times that of the Earth. That immediately tells you it's a lot less dense than the Earth. In fact, the density of Saturn is around 0.69 grams per cubic centimetre. Water is 1 gram per cubic centimetre. That means that Saturn is actually made of stuff that's less dense than the water we experience here on Earth. It's put in many children's books. If you could find an ocean big enough, you could float Saturn on it. So it's made of lightweight elements. This is the first indication it's made of things like hydrogen and helium, the lightest elements in the universe. Despite being so large, so, you know, 10 or so Earth diameters across, it spins at a very fast rate. We spin once round on our axis like this every 24 hours. Saturn, despite being so much larger, spins once round about every 10.5 Earth hours. So the whole planet is spinning much faster than we are. But it doesn't exactly spin exactly as we do, though. If I spin, my head and my tummy spin at the same rate. I'd have immense complications if that wasn't so, because I'm a solid body. When you look at Saturn, you find that the top here, around the poles, spins at a different rate from around the equator here. In fact, if you were at the top, at the poles of Saturn, you would find your day was 25 minutes longer than if you were at the equator. So that's another indication it's not a planet like Earth. Not only is it very lightweight, it's also not solid. This is called differential rotation, where bits of things move at different rates in their circulation. And it's a characteristic of, say, liquids or fluids. And that, again, is telling you this is not a solid planet. You know it's called a gas giant. It's made of gas, and it's gas not gas as we know it, but often really compressed, so it's almost like a liquid state. So this is mainly molecular hydrogen and helium. And the problem about it rotating so fast and being quite a lightweight planet is around the equator, matter gets flung out to the sides. And so if I draw a perfect circle on top of Saturn here, such that this is the polar diameter, you can see it's actually oblate. It's squished. It's the most squished planet of our solar system, such that if you are at the equator, you're about 6,300 kilometers further out from the center than if you're at the poles. So you've got a difference of about 10% in the width of the planet between the poles and the edges. So for all those reasons, it's a gas giant. And if we look at the surface of the disk, you're not seeing the surface of a planet as such. Here, you're seeing lots of clouds, all the upper layers of the atmosphere, all the clouds in the atmosphere. And as these generate storms and things, they are stretched. These storms are swept by the rotation to form these bands round the planet. So in terms of these upper layers, if we were to go perhaps just down those first few 100 kilometers within Saturn's atmosphere in the clouds, you can see various structures. Don't worry, there aren't going to be too many graphs. It will mostly be pretty pictures. But if we've just got some nominal 0 point, the real tops of the clouds, the very white-coloured clouds, are effectively mostly ammonia crystals that are frozen right at these very cold cloud layers. And the temperature there is about minus 150, minus 200 degrees. Now, as you go down into the clouds, it gets warmer. And a little lower down, you get clouds of ammonium hydrosulfide, a key term there being the sulfide. That means there's quite a bit of sulfur within these clouds. So that's one of the things that gives Saturn's clouds those lovely kind of orangey yellow glow. And then yet further down, you perhaps have water vapor clouds. And that's about the temperature of 0 degrees C. After that, though, you start sinking down into the molecular hydrogen atmosphere of Saturn. So if we cut into the Saturn, this is what it begins to look like as you go down. Out here, the outer layers of these clouds that I've just been talking about, where all the deep weather systems that we're going to be talking about are swirling around. Below that, if you carried on sinking through those clouds, you don't reach a solid surface until perhaps somewhere in the middle. You would just keep sinking. But the first thing you would notice is that the gas would get denser around you. Not just that, but it would get warmer. And you carry on sinking, and most of this outer region here is made of molecular hydrogen with a smattering of helium mixed in. Now, as you go down, the gravity gets stronger. This also means that all the clouds on top of you sink further down. You then have all the weight of these outer clouds pressing on you. And so as you go in, not only does it get warmer, you also get, you become higher pressure. Things get squeezed. And the weight of all this overlying clouds and atmosphere means that this molecular hydrogen is actually gets squished so far that it's in almost kind of a form like it's almost like an incompressible liquid. It's really dense. It's not like the molecular hydrogen we might expect in a lab here on Earth. It's much denser. And then if you carry on going down into the planet, I mean, obviously not with a nice sharp boundary as it suggests here, but it gradually changes into this very strange state of hydrogen called metallic hydrogen. This is where there's so much pressure that the atomic structure is broken down. The electrons in the hydrogen no longer orbit just around the hydrogen nucleus, but instead you have a whole bundle of hydrogen nuclei that share their electrons. And so we call this metallic hydrogen, not to mean that it's really like a metal, but it's got that sort of metallic structure of bonding. But because you've got all those free electrons floating around, it's a very good conductor of electricity. It's also swirling around at these enormous speeds. You're building up a dynamo, which is responsible for the really strong magnetic field that surrounds Saturn. And then as you go right into the centre, the temperatures are climbing. You've got a rocky core, and that rocky core is surrounded by a layer of, it's sort of soupy mix. We call it ice, but it's a mixture of sort of methane ice, water ice, ammonia ice. But that's just a thin layer, highly compressed, quite warm, and it surrounds a rocky core. Now, we don't know much about this. Obviously, we can't kind of dissect Saturn as we show here. We can only infer this by how spacecraft travel around it, what the gravity field is they respond to. And right at the core, we think it's about 5 to 10 Earth masses, probably made of similar materials to Earth, so sort of silicates and iron. But, you know, that's kind of guesswork. And that's probably the seed from which the planet grew as lightweight material accreted onto it. And that's at the core of the planet. And the temperatures down there are getting on for like 11,000, 12,000 degrees above absolute zero. So the centre of the planet's really warm. And this is interesting because it's warm not just because of all that weight of the outer layers. Saturn is strange that, in fact, it radiates more than twice the amount of energy that it actually receives from the Sun. So this is an infrared picture of Saturn. You can just see the ring's edge on here. This green is sunlight reflecting off the planet's surface because the sun is sunlight's coming in from kind of this angle. The red is showing you the longer infrared wavelengths. It's showing you heat rising up from the planet's interior. And this is coming from the core. And it is partly the heat of all the outer layers. It's not necessarily left over from the formation of the planet, though they could have retained a bit of that heat. It's producing far too much heat. So we think there's some clever mechanism about the way that helium and hydrogen change from this molecular to the metallic states halfway down in the atmosphere. And particularly helium's heavier than hydrogen, not by much, but enough, that you could condense out and it could fall through the hydrogen. And as it falls through, the sort of precipitation is falling under gravity. If things fall into gravity, they heat up. And there's enough of that changing going on that it produces this core heat within the planet. Now, this heat is important because that's what helps generate all these cloud patterns that we see within the atmosphere. If you look at Saturn, you've got these beautiful bands, and there are individual storms within those bands. Now, on Earth, we get weather because the sun comes in, it heats up the air masses differently, and they respond to whether over land or over water, and it's the heat input from the sun that provokes the motions of the air. You get that on Saturn, of course, but you also get the heat welling up from the inside. Not just that, of course, you have the rotation of the planet. You've got different strata of clouds and then bands of cloud that are rotating at slightly different rates from each other. And you can whip up enormous storms between all these motions. So, for example, one of the places where we tend to get very strong storms on Saturn is about halfway up. It's at a latitude around here. Just going to show you a picture in the infrared. It's been digitally sharpened a bit, and infrared allows you to see deeper into the clouds than visible light. But here you can see a whole slew of little hurricane storms growing within this kind of band on Saturn. These are going on all the time. A lot of them are temporary structures. There are much bigger storms that happen on Saturn. Here's one from 1990. You may not even recognize it as a storm because it's this white band here. This is known, I know it's not very spot-like, but it's known as a great white spot. And this is kind of semi-periodic phenomenon that happens in the atmosphere of Saturn. There's been one just recently that started to appear last year. This is an early picture of the storm here. It's almost like you have heat. It rises up through the clouds, and then as the material freezes out in those frozen cloud tops, you get the crystallization of the ammonia structures, you produce this white cloud. But then the planet's rotation kicks in, and it smears this sort of thunderhead, if you like, right around the planet. And it soon wraps around to form a band, and you get quite long-lived structures. The scale of this, by the way, is of the order of sort of 15,000 kilometers that way, and you're getting on for sort of 300,000 kilometers in length. And we can study from Cassini how these storms, we can't necessarily find out why they occur, but we can watch their development. We think that because this happens at a certain time within Saturn's orbit around the Sun, Saturn is inclined relative to the Sun. So sometimes the southern hemisphere faces the Sun, sometimes the northern hemisphere faces the sun. We're reaching a point where the northern hemisphere is beginning to face the sun, and that seems to be when this great white spot occurrence occurs. So it's something to do with the warming up of the seasonal change within Saturn's northern hemisphere. And of course we can map out, we can study the development of these storms. Here's the great white spot. Now these are garish false colours because they're infrared mappings. Again, you see deeper down into the clouds, you can see much more of the sort of vertical stratigraphy and structure of the storm as it develops. And this is how it just changes from one appearance to the next rotation, so just like sort of 10.5 hours apart. And these are a meteorologist's dream. These are pure storm vortices. You don't have any of those complications of land or sea that confuse the storm systems on Earth. You can watch storms in their purest form develop and grow and change on these gas giants. But where there's the really biggest storm, well, okay, there are two big storms. If you look right down at the South Pole here, there's an enormous hurricane. It's probably about the size of the Earth, could be swallowed up within that storm. And here's a time lapse just from looking down onto the top of that storm, sort of different pictures. And you're looking down, it's got a very clear, well-defined eye wall. But it's whirling around so fast, something like 500 kilometers an hour. It's sort of twice the speed of a Category 5 hurricane on Earth. But that is nothing compared to the storm that's on the other side of the planet, on the northern hemisphere. Here we have a storm. I hope you can see it. Probably a bit faint now. Just show you again some enhanced images looking right down on the pole. You have a hexagonal storm. Now again, this is big. You could fit 4 Earths into that hexagon. Voyager saw this storm in 1980. It's still there now. Cassini's been looking at it. It's a very stable structure. It's the only known hexagonal storm in the whole of the solar system. And of course, it's a challenge to see if we can explain that. And there have been simulations in the lab. I'm just going to show you a little movie of an experiment done by Anna Barbosa-Arguello and Peter Reed at Oxford University. So where in the lab, they have a big tank, about 30-litre cylinder that's rotating. That resembles the rotation of Saturn. And in the middle, they've got a much faster cylinder that's spinning. And they've just injected dye. And what happens is the relative motion of the big bulk of the water swinging around and this tighter spinning cylinder in the middle is it builds up eddies on the edge that then push the fluid flow to form a perfect hexagon. And you get different polygons depending on the different relative speeds of the spinning cylinder and the outer rotating material. So this could mimic a way a jet stream is set up within Saturn's rotation of the rest of the atmosphere, and it develops this kind of structure. So we're not saying this is a definite solution, but certainly it seems to be the best guess yet. So fantastic structures just within the clouds of Saturn. But of course, that's not really why we all love Saturn. We love Saturn because of its rings. These enormous structures. I mean, other gas giants have rings, but they're nowhere near as spectacular. It's larger as bright as Saturn's rings. And obviously, they don't just kind of go around in an arc like that. This is the shadow of Saturn being cast over the rings with the sun coming in to the left. And these rings span a distance from just over 6,000 kilometers above the planet's surface, way out to about 120, 140,000 kilometers till you get to these outer rings. And that doesn't mark the end of the rings, they go on beyond that. And fantastic structures. They're all completely flat. Despite being this huge scale, this is an edge-on view of the rings from Cassini. What you're seeing here is sunlight coming up this way. This is the edge-on view of the rings, a little moon there, and this is the shadow of the rings being cast across the hemisphere of the planet. If you were to put all of Saturn's rings and shrunk them down to something like 2 kilometers across, the width of the rings would probably be about the width of a piece of paper, a piece of A4 paper. They're incredibly flat. So despite being this enormous size, they typically average about 100 meters in thickness, or in thinness, I should probably say. So very, very fine structures. And within them, there are fantastic variations. They also vary as to how we see them. And this is what flummoxed Galileo. When he first saw the rings, probably they were at an inclination similar to this. They then appeared to disappear, and then he could see anything in sort of 1612 when he was looking, and then the rings then open up again, and he could then see them as these handles. This is what we believe he saw. And Saturn changes over a period. And again, it's to do because the fact Saturn is inclined to not just the Sun. In fact, I've got a diagram that shows it. Saturn is inclined relative to the orbit and the plane of all the planets. So sometimes we see the rings so that they're completely edge-on. Again, it depends on our viewing angle. And sometimes we see them face-on. And as it goes round, so if you can see with my hand here, sometimes you see them and sometimes you see them edge-on. It really varies as you go round. And the last time we saw them edge-on, we call this a ring plane crossing, was September 2009. So if you wanted to look at Saturn, the rings don't look very dramatic at the minute. And if you do want to look at Saturn, you've got to be up about 10 to 5 in the morning with a very clear eastern horizon. It's not very observable at the minute. But if you did, you would see the rings are not very dramatic. If you can wait perhaps till about October 2017, they're going to have opened up quite a lot more. But they're going to be spending all that time from 2009 to 2017 getting bigger and brighter. And at that point, they'll be about as flat onto us as they can be. And that changes the whole brightness of the planet by, it's about half as bright again when you get the reflection of the rings involved as well. And so it goes through this cycle as it goes around the Sun of the rings appearing to close up and open up and close up. And it's the same way that we see first Saturn's southern hemisphere and then Saturn's northern hemisphere tilted towards us. And the rings, they have names. They have, I'm afraid this is a lovely departure from astronomical tradition of naming objects. They're called things like A, B, and C. We have all these wonderful names for moons and craters, and then we call the rings A, B, and C. Now, this is just some idea of the chronological order of their discovery. So there's A, B, and C, the primary rings. These are the ones that, say, Cassini was mapping out, in particular, the fact that there's a division, a dark line between the A ring and the B ring, and in fact that division's named after him. And then there's also a big gap within the A ring that's very clear of material. And these rings change in terms of, we can map out how fast they rotate. Rings right on the inside of the C ring go once around Saturn about every 6 hours. By the time you get out to the outside of the A ring, you're looking at orbital times of getting on for 15 hours. Again, it's not one solid body rotating. Every little ring has its own orbit, has its own time taken to go round. Because these rings are not solid structures, they're masses of ringlets. And even within the ringlets, you can get variations of sizes of particles. Here, for example, you're looking through the A ring. Here. The A ring is quite transparent. You can see through it down to the cloud tops of Saturn below. The B ring is much more opaque. The C ring is very dark. And you've got different brightnesses depending on what's involved. So the C ring is much darker and dustier. And you get the B and the A ring, sorry, the B ring is much more opaque. And it's to do a lot with the size of the particles within them. So if we stretch further out, the D ring was then discovered. It's the darkest ring is basically within the C ring, and out beyond the A ring we have this thin band known as the F ring, which was discovered by Pioneer 11 in 1979. And out beyond that we've got a very fluffy diffuse E ring, and out beyond that there's an even bigger ring that was only discovered about 3 years ago. And the characteristics of all these rings are that they're very shiny. That may sound a very trite comment, but it means if something's reflective, it means there's a high proportion of water ice. And when you look at the reflectivity properties of these rings in different lights using Cassini and also instruments on Earth, you can get an idea of the sizes of the particles for the rings. So by the time you get down to the D ring, you've got particles that are tiny. They're about the size of microns. By the time you get to the C ring, they're maybe a bit larger. They're like grains of sand, perhaps the odd sugar cube. The B ring and the A ring, you've got all those small particles, but you've also got larger lumps, about the size of pebbles or cobbles and the occasional small boulder. And all of this material is a high percentage of water ice along with the rock. And we believe it's the remains of a shattered moon. One little moon got too close to Saturn, got pulled apart by the differential gravity of Saturn into millions, billions of these pieces. And because they're so close to Saturn, again, the gravity stirs them up all the time. It stops them from aggregating into any structure. They're just spread out continuously. And there's enough matter in those rings that we think maybe the original body was about 300 to 400 kilometers in diameter. And maybe it was shattered about 100 million years ago. These rings are pretty clean. They're not that old. So they're relatively transitory. Well, you know, this is astronomy. Don't suppose you call 100 million years really that transitory, but never mind, relatively transitory feature. And there are various gaps named after scientists making up for the A, B, and C nomenclature of the actual rings. And here you can see some of the structures of the rings. But the particles within these rings show variations. When the rings are horizontal to the sun, you get the longest shadows cast. So it's like at sunset, you get the longest shadows cast because the sun's low down in the sky. When the rings are horizontal to the sun, again, you get the longest shadows cast. This is a view down onto the rings from Cassini with the sun coming horizontally across. And first you can see a shadow here of the moon Mimas, which orbits just outside the rings. What I also want you to note, maybe you can see just along here, if I just blow that region up, there are shadows cast by structures within the ring. So even though telling you they're really flat and they're really small particles, there are perturbations where particles are grouped together to form sort of just piles that rise up. In this case, maybe from about 1/2 to about 3 kilometers up, that are high enough to cast shadows on the rings. And we see these throughout the rings, but particularly at the edges. Here's another couple of examples. So this is that anchor gap here. If I blow up there, you can see ripples and structures and heights within the rings. And these are temporary disturbances, and they are caused by little moonlets that orbit within the rings. There's a very much clearer case just a little bit further out in this Keeler gap, which is this very thin gap right at the edge of the A ring. If I zoom in on that, it's almost like we call them propeller type disturbances. There's a little moon in there called Daphnis. You can't actually see it. It's slightly tilted relative to the rings, so sometimes it pulls material in the rings up, sometimes it pulls materials in the rings around. And behind it and in front of it, it causes perturbations, it causes dynamical variations in the structure. And we see these throughout the rings, these propeller structures, just alerting to the fact that these large fragments are called moonlets within co-orbiting with the rings. And here's a clearer picture. There's Daphnis. There we are. It's only about 8 kilometers across. It's tiny. And it's responsible, really, for the whole of this gap. It clears out the gap. It's what's known as a shepherd moon. It herds the particles. It sorts them out. It's got a clear passage through the rings just on its orbit round here because it's cleared that space. And there are other shepherd moons. These are the really small moons around Saturn. There's a lovely case of interaction with that outermost ring, the F ring. Look at this in-depth picture of it. It's all kind of braided and twisted. And this is the gravitational effect of a little moon called Prometheus. Slightly bigger than Daphnis. It's about 100 kilometers across. And it interacts with this ring and creates these ripple structures. Here is the F ring. So before I was talking about Daphnis in this gap. Here's the F ring, and you can see a repeated pattern within it. And it's being caused by this little object. If I zoom in on that, that's Prometheus. And Prometheus orbits within the rings, but it's got a slightly elliptical orbit. It goes around every about 14.5 hours. And it's furthest from Saturn, it's far enough that it just almost like kisses the F ring. It gets so close to it that its gravitational pull, even though it's a small moon, can disturb the particles. And it can pull out a trail of particles behind it. In fact, here's a little movie of it in action. So just at the outer part of its orbit, it comes up to the ring, and it'll go dark for a couple of minutes. The video will come back. You see it begin to pull material out, and then just causes a ripple behind it. And it's doing that continually. And each time it comes, I mean, the thing is, it's going around in its orbit slightly faster than the F ring is rotating. So each time it comes and meets the F ring, it meets it slightly further on, because the F ring doesn't catch up with it. And so it progresses, it sort of hits here, hits here, hits here, hits here, and it leaves in its wake all these little ripples. And these ripples die out, they're temporary structures, and by the time the Prometheus comes around again, it's got a nice smooth ring to then go and disturb again. So you get these fantastic structures within the rings, and again, dynamicist dream, all these different gravitational interactions. So we move to the moons, and there are of the order of 62 moons around Saturn. It depends when you start deciding something's a moon or a moonlet. You start including the moonlets, there are probably many, many more. Out of all of those, 38 of them are pretty small and irregular. There are only 13 that are actually above 50 kilometers in diameter. Most of them are pretty small. And there are only really 7 big moons. I'll just ring them here: Mimas, Enceladus, Tessis, Dion, Rhea, Titan, and Iapetus. All the rest of them are pretty small. You've got the shepherd moons that are involved with the rings, and then you've got some very irregular moons. So in terms of I'll talk about the main moons later, but let's just go through some of these small ones because they're weird. You've got Phoebe. This is the outermost moon of Saturn. It's very irregular. It's very dark. And it doesn't just have a kind of pitted surface, very heavily cratered surface, deposits on the surface. It also orbits the wrong way. All the moons and the rings orbit around Saturn above the equator. Phoebe does its own thing. And not just that, they're all orbiting this way, and it's going the wrong way. So, it's like patting your head and rubbing your tummy at the same time. Come on. But it goes what we call retrograde. It goes in the wrong direction. So for all these reasons, we think it's a captured object. It wasn't originated with Saturn. It's been pulled in by Saturn's gravity later. And in fact, many of these irregular objects we think are accreted objects, maybe like Phoebe from out, say, in the Kuiper belt beyond Neptune. Here are 2 other strange objects, Prometheus and Janus. They orbit quite close to the rings. They're about the same size, 110, 120 kilometers across, very similar composition. In fact, we think they may be part of the same original body. But they've got the weirdest orbits. They orbit more or less together. Now, this diagram's not to scale, because these are each about 120 kilometers across, and they're about 90,000 kilometers above Saturn's disk. But the key thing is they orbit only about 50 kilometers apart. So the one that's on the outside goes slower than the one on the inside. And what happens is every so often, every 4 years in fact, they come alongside. Now at that point, they don't collide, despite being less than half their width apart. They do this weird thing where the moon on the inside that's travelling faster pulls on the outer moon, speeding it up. The moon on the outside slows down, pulls on the inner moon, slowing it down. And Kepler's laws of gravitational motion, which I'm sure you're all terribly au fait with, but basically what it means is if you travel fast, you have to be at a lower radius. And so what happens is they swap. And they do this every 4 years. They never collide, they just exchange orbits and then go on their way and then exchange their orbits. The only known double moon system that does this within our solar system. Utterly intriguing that they've got themselves locked into this pattern. And then many of the other smaller moons have their own irregularities. Some, like Pandora Telesto, we think are probably more almost like loose accumulations of rubble all held together by some granular icy material. We don't really know how solid they are. And then the weirdest of the irregular objects, here, Hyperion. How does this become a moon? What is this? You can see it's cratered surface, but they've got really sharp edges. The whole thing it's about 250 kilometers across, but it doesn't orbit about any one axis. It's got this really chaotic rotation. It spins around one axis, then another, different rates. It's tumbling again. This is unlike any other moon we've seen in the solar system. We can only assume it's some kind of captured object. So if we now move to the 7 main moons, the smallest of them is Mimas, and it's only about 400 kilometers across. You can see it in the distance beyond the rings here. And it's got a humongous crater on. This crater, it's called Herschel after the discoverer of Mimas, it's about 130 kilometers across. To put that in context, if on the Earth we had a crater that large, it would be larger than Canada. Okay? You have to look at this and wonder how Mimas survived this impact. You might also look at this picture and think, that reminds me of something. Perhaps that. In fact, though, the best pictures of Mimas showing this large crater were actually discovered years after the start of the Star Wars trilogy. So unless George Lucas knew something we didn't know about Mimas, unfortunately I don't think it did account for the inspiration, but nonetheless it's quite an uncanny similarity. And around the back of the moon, I hope you can see, it's kind of got fractures within the surface, implying this was a massive impact that probably almost destroyed the moon that created that huge crater. And Cassini's been looking at the crater. There's a lot of water. This moon, like all the moons, is mainly water ice mixed with rock. Here you can see it's mainly ice, and it's excavated this crater, but along the bottom of the crater walls there's a dark line. You can see dark material spilling down the crater walls. So within this ice there are silicates, so like soot and sand, carbonates and silicates, buried, impurities buried within the ice that are then exposed when a crater hits. And as the ice is exposed, maybe it sublimates away and this dark material sinks down to the bottom of the crater walls. Even on some of the smaller craters around the side, they show similar effects. The biggest moon around Saturn is Titan. At, just over 5,000 kilometres across. This really is big. It's bigger than the planet Mercury. It's only a moon because it's primarily in orbit around Saturn rather than around the Sun. And you can see it's peculiar, not just because it's large. It's the only moon in our solar system that's covered with a really dense atmosphere. So dense that you can't see features on the surface. And indeed, we can only see through it using radar mapping, which is one of the ways that Cassini can investigate it. This atmosphere is mainly molecular nitrogen. Molecular nitrogen, perhaps 98%, and then there's quite a bit of methane. The remaining is methane. And right at the tops of those clouds, the UV radiation from the sunlight breaks down the methane into the carbon, the hydrogen, the nitrogen, and then it builds into really complex hydrocarbons out to give this kind of haze here. It's, that surrounds the outer layers of the atmosphere. And then as you sink down into the atmosphere, it's a lot of molecular nitrogen, again with lots of very complex hydrocarbons, particularly methane, ethane. And when we look at the surface of Titan with radar mapping, you can see structures. This is a continent about the size of Australia. We call it Xanadu. Doesn't quite look as glamorous as you might hope Xanadu would look. So you can see structures on the surface. There are lakes on Titan. Titan is freezing. It's about minus 180 degrees. These aren't lakes of water. That temperature is about what we call the triple point temperature for methane. Instead, we think, so like we have a water cycle here on Earth where you have water vapor, water liquid, water ice. Here on Titan, we have a methane cycle. So you have methane clouds, you have methane rain. And on the surface, you have the occasional methane lake, liquid methane. So this is a false colour image. It's radar mapping. Where it's black, it returns a different signal, meaning you've got a very flat reflective surface to the brown. And so these dark patches indicate where there are lakes on the surface of Titan. And there are at least 400 lakes that have been mapped out across the surface of the small moon. These lakes can have tributaries. They can have a crenulated structure, almost like sort of fjords around the outside. And we can also see the weather patterns change. Here are two images a year apart. You've got different cloud structures, which are the white. The dark is the lakes. This is Ontario Lake. It's a big lake in the southern hemisphere. But you can see lakes that come and go, maybe as a result of methane rain. So we're actually watching the weather on Titan. And we can see other structures. We can see sand dunes. You get, well, okay, not sand dunes, probably not sand, but dunes nonetheless. It's probably some really murky organic material instead. So just like we have dunes on the Earth, and yes, this is the Earth, we have dunes around the equator on Titan. That means there are strong winds there, okay, to create the dunes. We can see craters on the surface. We know quite a bit about Titan. This is an artist's impression. Get absolutely clear. because just after Cassini got there, it dropped a little probe named after Huygens, one of the early observers of Saturn. And it took about 2.5 hours to parachute down through the clouds. And it reached the surface. It didn't know what it was going to find. It was even possible it was going to land on a lake. And it sent pictures on the way down, here mapping dry lake beds, tributaries and dry river channels, presumably cut by that liquid methane clouds. And this is a picture from the surface. Glorious tangerine colour. It landed on what we think was a frozen lake bed. We know that there's liquid methane that's flowed over the surface. If you look at these pebbles, and so these would say that's probably about 10, 15 centimetres across, you can see they've got shallows underneath them. Something liquid has flown over the surface and excavated shallows round under those stones. So it looks like there's been liquid methane over the surface where it landed. So a fascinating moon. We think it could be a very good case, an example of maybe what very early Earth was like. Obviously, but just preserved out in the deep freeze of space without any of the chemical reactions that then, over the ensuing billions of years, turned our Earth into the habitable planet it is. And then we've got all the these look a bit more like you expect moons to look like. They're mixtures of rock with quite a lot of ice again, Tethys with its huge crater, scarred surfaces. There's no wind, there's no atmosphere, there's no erosion to wash out the craters. Deep canyons in the ice on the moons. Rhea with one of the most pitted surfaces. Here you've got a relatively new impact that's thrown lots of reflective material out. And Dione, which strangely has one side very cratered and one side not very cratered. And it's not how you would imagine. A lot of these moons are locked so that their orbital speed is the same as the time it takes them to go once around. So they always have the same face towards Saturn. So with something like Dione, you would expect if it's going around Saturn in this direction, this is what's known as the leading edge. It kind of collides with anything in its way. You'd expect that to be where all the craters are. It's the wrong way round. Maybe this means that at some point, quite late on, so it's had all this cratering, and then it's had an impact which has knocked it round about 180 degrees, and so it's now got the smooth edge the wrong way. Curious things that could have happened to it. But then two last moons that are just really altogether strange. Enceladus is an ice moon. It's one of the shiniest objects in our solar system. You know from the nature of the light that's reflected, this is almost like pure water ice across the surface. And this is why it's not as heavily cratered as those rocky ice moons I've just shown you. You can see some craters up here, but virtually no craters down here. Now, all these moons are subject to impacts on the surface, creating craters all the time. The fact that it's got part of the moon that's very smooth and uncratered means it has been recoated. It's been recoated by warm ice, cold water, that has somehow spread over the surface and resurfaced it, filled in any craters. And we think this ice comes from under the surface, this warm ice, this cold water, and it leaks out of these fissures. So have a look at the surface. Here are old craters. Here are some of these new fissures that overlie those craters. These are much more recent. And the whole of the surface is still evolving, is still changing. It's not quite tectonics, but there are movements within the water ice. And these are revealed by some of the shapes of the fissures and the cracks within the ice. So, for example, if you look at these three lines come up and then turn through 90 degrees as if the whole area has been switched round. And again, just structures here. You can see long linear structures and then turned right round. So this is a surface that is still quite young, that is still changing. And not just that, you've actually got something, if you step back and you look at Enceladus from a distance, you've got something very strange going on. This is a picture taken from Cassini, doing one of its swoop paths of the surface of the planet. And you can see Enceladus is spraying out material. It's spraying out water vapour and ice crystals hundreds of kilometres above the surface. Now, some of this will be some of this will settle down back onto the planet and be partly responsible for that recoating of the surface. And we believe that these jets that you see, I mean, they're just apparent in this image, obviously, because this is backlit. You've got the sun coming towards us, and it's just lighting up the sprays, whereas Cassini's in the shadow of the moon. And we think they come from these deep fissures that we dub the tiger stripes of Enceladus. So if you do thermal imaging, so you test the temperature of the surface around these stripes, you find the stripes are warmer. So here's a temperature map where going from the purple right through the pink to the yellow gives you a difference in temperature. And you find that along these deep fissures, the temperatures can be above, about 100 degrees above the surrounding surface. And that's telling you that these fissures are probably where those jets, those big plumes, are coming forth. And we think the reservoir for that material that's issuing forth comes from a subsurface ocean underneath this ice. This is just a schematic of what we think is happening. At the centre, you've got some rocky planet. This rocky planet is a fairly large moon. It's quite close into Saturn. It undergoes what we call tidal stresses. It gets squished and it gets squeezed as it goes every time round its orbit round Saturn. This keeps the core of the planet warm, not boiling hot. It's not got a molten core. It keeps it warm such that the layers above it are a liquid ocean. And then right out when you get to you get down into outer space, the ocean is frozen and you've got a surface layer of ice. We think that this provides a reservoir for those jets in the sense that down at the rock, you're going to get salts and minerals start dissolving, start leaching into the water, into the ocean. Under pressure, this water is pushed either by bubbling, I mean there are lots of different ideas, but it actually creeps up through fissures and cracks in the ice into caverns that we think are just below the surface, and then is forced out through these cracks, and maybe they temporarily open up and close. We don't know how this changes really over longer timescales. And this material is sprayed out into space. And the thing is, we know, the reason we think there's a liquid ocean there is that when Cassini flies through these plumes, here's a picture it took just a month ago. In one of its passes, it can actually go through these plumes. It's got sensors that allow it to almost like taste, to sample the material in the plumes. We know there's salt in there. We know there's things like bicarbonate of soda, if you like, baking soda. To have salts in this water spray means you need a liquid ocean that's been in contact with rock to leach out those minerals and salts. And then they get blasted out into space. And so that's a good indication of this liquid ocean that we think exists under Enceladus. Now, some of these fall back onto the surface, but a lot of this sprays out much further. And in fact, Enceladus is responsible for the E-ring. This is the light, fluffy ring, so it's probably not a very technical term, a tenuous ring. A much thicker, tenuous ring right outside the others. It's very broad. And this is Enceladus right at the centre. And all the material then gets dispersed and left behind. And it gets pushed on by the sunlight. It gets dispersed to form this very broad ring. One large moon left, Iapetus. It's the furthest one out. It's probably about sort of 3 times further than all the rest of the main moons around Saturn. And this was one of those ones discovered a long time ago. I'm trying to remember, in 1671, I think by Huygens. And even looking at this moon through his telescope, he knew it had one black side and one white side. Because every time it was on one side of Saturn, he could see it. When it ran to the other side of Saturn, it disappeared. So you've got a moon where one side is ice, reflective, reflects 60% of the light on it. The other side is completely dark. And not just that, it's got this sort of walnut ridge around the centre that's about 13 kilometres higher. Some ideas it could be a ring that's collapsed onto the planet, or it could be some amazing sort of tectonic activity. But again, we don't see any other moons in the solar system that have, the equator is here symbol, nicely marked around the outside. And the question is, why has it got this two-tone effect? If you look at regions sort of on the boundary between the ice and the dark, you can see that it looks like material is actually, there's black stuff overlaying the ice. So what we think is there's dark material that has been accreted by Iapetus. Now, if you have some seed material that's accreted onto the surface, it's actually got a very long day. It's got a 79 Earth day long Iapetus day, which means that if you get a dark spot on the surface, it's exposed to the sunlight a long time, it heats up a lot, it warms the surrounding area, the ice sublimates away. So as soon as you've got a seeding of dark material, then you get a runaway warming effect that then creates one dark side. The other side stays cold because it's reflective, and so you end up with this runaway effect. The problem is, where did this dark material come from in the first place? There are ideas of volcanoes, ice volcanoes within Iapetus, but we think the culprit is actually Phoebe. Out way beyond all the moons of Saturn, there's one last ring. It was discovered only a few years ago in the infrared. It's a dust ring. It's not made of water ice. It's a very extensive, thick ring. And it follows the orbit of Phoebe exactly. Remember I told you that the rings and the moons are like this, and Phoebe's doing its own thing. Well, this dust ring is in exactly the same orbit. And we think it's created by micrometeorite impacts just kicking off dust. And what happens to poor Iapetus is it goes through that dust, and it's almost like, flies on the windshield. It gets this dust splattered on its leading edge and coats it with dark material and leads to that runaway effect. Okay, so we're almost at the end. Just one last picture I have to show you. Backlit, yeah, I love it when you all say wow. It's a beautiful image. Backlit photo of Saturn from Cassini, and it's just got all the rings lit up from the sunlight. Another reason for showing you this picture is that you are, and this smile, you're on camera. Bet you can't see it, especially if you're at the back. We are somewhere up here. Let's just zoom in. This little dot is the Earth. Now, it doesn't mean that we're a moon in orbit around Saturn. You're obviously kind of looking through the rings right to the distance of Earth. But so we'll just leave you with, this last picture of us, planet Earth, as seen from Saturn. And this is not really where we're going to leave Cassini. I've shown you all these wonderful images. There are many more available. There's a website here that is a source for many of these pictures. We will go back to Cassini. If any of you are free in 3 weeks' time, come along and hear about the sounds of the universe. And you will hear the sounds of Cassini passing through the rings of Saturn. And not just that, but we'll also listen to the sounds of that Huygens probe as it descended through the atmosphere. It had little microphones, and you will hear the winds on Titan. So hopefully it's something to look forward to in 3 weeks' time. Thank you.
Mine was, I hope not a silly question. What use is Saturn to us?
Have you no soul? Okay, sorry, that was a very facetious remark. A very rude remark for which I probably...
It was a serious question. I mean, what does it hold for us?
What does it hold for us? Okay, what it holds for us, it's a test bed for both meteorology. If you had one of my colleagues here talking about, if you have a dynamicist who works on the mathematics of orbiting particles, Saturn's rings, the interaction between the rings and the moonlets are a dream. Just understanding all these structures we see, how ensembles of particles move. It's a wonderful test bed to try. Can we predict, can we reproduce what we see? Also trying to understand the diversity of the moons, looking at what they can each of those moons can tell us about the history of the formation of our solar system, all the impact scarring on the moons. It tells you something about the early bombardment of debris on the moons. You've also got meteorology of Saturn's atmosphere. And then you've got things like Titan, which, as I say, we think is very closely resembles what Earth maybe was like, 4 billion years ago, except none of those chemical reactions have taken place. So I think we still have an awful lot to learn. And if that doesn't convince you, wait till the day when NASA or any other space agency work out how to send a probe to land on Enceladus, melt through the ice, and start exploring the subsurface ocean. Liquid water, warm environment, possible environment for life. You never know. So, could be very interesting still to discover.
It seems a great pity that space programs are being cut back at the moment when there's so many interesting things still to be discovered. For how long can Cassini keep going, and are there any plans for a replacement or an improved version?
Unfortunately, I'm not aware of any plans for an improved version. The next large planetary mission hopefully will be revisiting Jupiter, and even the funding of that's very much in doubt because the Americans have pulled out. In terms of Cassini, I think it's been renewed probably until the end of next year, maybe a bit longer. But as long as it's functioning and we're still getting amazing results out, they're going to keep operating. And this latest renewal, of course, allows us to see the onset. We're getting to the point where, as I said, the northern hemisphere is now being illuminated by the sun. And so we're hoping to track new seasonal changes within the atmosphere of Saturn and just see the change. So just see how it changes the weather systems within the clouds. So.
Mine's just a simple question. When a meteorite hits Saturn, what happens to the material when it hits the outer atmosphere of the hydrogen and helium?
Okay, we can answer that question, not because we've seen it happen on Saturn, but on Jupiter, we've quite often seen impacts, onto, or rather into Jupiter. You may remember in July 1994, quite a while ago, but there was a broken up fragment of about 20 broken up fragments of a comet called Shoemaker-Levy 9 that fell onto Jupiter, and they kind of punched enormous holes within the atmosphere. So I'm just using Jupiter as an analogy for Saturn because we think it would be similar. What happens to the material is that the object disappears from sight, but then there's this enormous black scar that bubbles up. And that is like a plume of debris, because the object that falls in, it never reaches the rocky core. It gets pulverized, it gets squeezed, it just gets completely pressured, and it will then kind of completely vaporize. And all the material from the comet or the asteroid then comes out in this warm debris plume that then bubbles up and breaks out to the surface. It creates this dark impact scar, which lasts a while, a few weeks, but gradually, again, you've got those winds on Jupiter as on Saturn, it gets eroded and gets blown away, and the object has just been completely swallowed up by this gas giant.
I must stop you, all of you. I think we chose well. Thank you very much, Carolin.